All right, let's dive in. Today we're looking at something that honestly sounds impossible. The term is hot ice.
Right.
And it immediately raises a flag, doesn't it? How can something be like ice, a solid crystal, but also be hot?
It's the ultimate paradox, and you can see why the source material you sent over calls it chemical magic, but
Right.
really, it's just fantastic chemistry.
Okay, so our mission here is to demystify this, to figure out what's really going on.
Exactly. And the first thing to get out of the way is that we are absolutely not talking about water ice. This is something else entirely.
Right, this is not some violation of the laws of physics.
No, no. This is a scientific phenomenon, but it's not a natural one. The key ingredient, which our sources all point to, is a chemical called sodium acetate.
Sodium acetate. Got it. So let's talk about how you even make this stuff. The sources lay out a preparation process that seems, well, almost too simple.
It is surprisingly straightforward. You start by dissolving a huge amount of solid sodium acetate into a little bit of water.
So you're making a really, really concentrated solution.
Super saturated, yeah. Then you gently heat it up until every single one of those little crystals dissolves, and it's just a clear liquid.
And then comes the critical part, according to the notes, the cooling.
This is everything. It is the most delicate step. You have to let that solution cool down really slowly, and crucially, it has to be completely undisturbed.
So no shaking the table, no dust falling in.
Nothing. And what you're left with is a flask of liquid that looks just like water. But chemically, it's a trap waiting to be sprung.
A trap. I like that. So it's sitting there, cool to the touch, but full of potential energy.
Yeah.
And the sources say you just touch it, and it instantly becomes a solid.
That's the spectacle. The moment you touch it, a wave of crystallization just spreads through the whole thing. It turns into this solid, icy-looking structure right before your eyes.
Which brings us to the core science of it. Because that kind of reaction speed, it's incredible.
It is. And the term for it, the engine behind all this, is supercooling.
Okay, supercooling. This is where it gets really interesting.
So normally when you cool a liquid below its freezing point, what happens?
It turns into a solid.
Right. But with this sodium acetate solution, when it cools down, it actually drops below its freezing point, but it stays liquid.
So it should be frozen, but it isn't.
Exactly. It's defying what it's supposed to do. It's sitting in this highly unstable state that scientists call a metastable state. It wants to freeze, but it can't.
Why not? What's stopping it?
It's blocked because it needs a starting point. Think of it like this. For molecules to line up and form a crystal, they need a blueprint, a little seed, a nucleation site to build around.
Ah, okay. So by cooling it so perfectly, without any dust or imperfections, we've basically created this pristine environment where there's no blueprint. The molecules are lost.
Precisely. They're all ready to lock into place, but they don't have that first piece to connect to. They're just waiting for a simple shock.
The shock that the sources mention.
Right. A simple tap on the glass or dropping in a single tiny crystal of sodium acetate.
And that's the catalyst. That gives them the permission they need to start building.
And once it starts, it's a chain reaction, a cascade. The whole thing solidifies almost instantly because it's so far past its tipping point.
Okay, that totally explains the ice part of the name, the instant solid, the crystal structure. But now we have to tackle the hot part, because everything I know about freezing says it should feel cold. You're removing heat.
And this is the core of the paradox. Water freezing requires you to take energy out of the system. This is the opposite. The crystallization of sodium acetate is an exothermic reaction.
Exothermic, meaning it releases heat.
It releases a lot of heat. Remember the very beginning when we heated the solution to dissolve the crystals?
Yeah.
You were pumping energy into that system. That energy, that latent heat, gets stored in the bonds of that unstable liquid.
Like compressing a spring, you're storing potential energy.
That is a perfect analogy. And when you finally trigger it, when you provide that shock, the spring is released. The molecules snap into their stable, low-energy crystal form, and all that stored heat has to go somewhere.
So it comes rushing out into the surrounding.
Exactly. The sources say the temperature of the reaction rises pretty dramatically.
So how hot are we talking? Is it dangerous?
Not really scalding, no. Usually somewhere around 130 degrees Fahrenheit, maybe 55 Celsius. It's definitely hot, or at least very warm to the touch. Nothing like regular ice at 32 Fahrenheit.
And that completely solves the puzzle. Hot ice. It looks like ice, it forms like ice, but it feels hot because of that exothermic energy release.
It's a name based entirely on the physical experience of it.
It's basically chemical performance art, Which explains why it's so popular for demonstrations.
Oh, absolutely. The visual effect is incredible.
Yeah.
You can, pour the liquid onto a dish, touch it, and a tower of solid crystals will grow right up out of the liquid.
And because it solidifies as you pour, you can literally sculpt with it.
You can.
Yeah.
And that leads us right into its most common practical use.
The reusable hand warmers, of course.
That's the one.
The little pouches with the liquid inside that you click.
Exactly. When you boil one of those to reset it, you're doing that first step we talked about. You're dissolving the crystals and storing all that latent heat energy inside the liquid.
And it just sits there in that supercooled state, waiting for you.
Indefinitely. All that stored warmth is on standby until you need it.
Which is just, a brilliant little piece of engineering. So to wrap this up, what have we learned here?
Well, you now know that hot ice isn't magic. It's sodium acetate.
Right, and it relies on the principle of supercooling.
Supercooling, yeah.
Hmm.
Staying liquid below its freezing point. And the crucial takeaway is that its transformation from liquid to solid is an exothermic reaction. It releases stored heat.
Which is why it feels hot.
That's the whole story.
That was a fantastic deep dive. So it all comes back to those hand warmers. We know supercooling needs a physical shock to get started. And inside those hand warmers, there's always that little flexible metal disc.
The famous clicker, yep.
So here's the final thought. Building on everything we've just discussed about needing a shock, a nucleation site, what do you think is actually happening physically when you bend that little metal disc? What is that click doing to kickstart the whole process?
It's a great question. It all goes back to creating that very first seed for the crystals to grow on.
Something for you to look into. We'll catch you on the next deep dive.